Uh-huh. Is that up at the Union or here at the...
Well, downstairs.
Oh, they're gonna send me those, so they have it.
Okay, this will be a little shorter lecture today since we have another talk right after. And also, it's kind of a difficult lecture because I'm going over the very details of all the computational that we need to proceed ahead in doing atomic physics, but mainly when it comes time to do the molecular use of Young tableaus and things like that. The things we'll talk about today are really important and very helpful. So the first thing I would like to do is, first of all, remind you we have these things up to date. And most of the stuff that we're talking about comes right out of these first couple of, well, actually three phys revs that you can click on and get a pretty good copy of for a price of 0.0 approximately. Okay, these are papers that we add occasionally, but the main thing I want to get started with today is using the matrix that we worked so hard to calculate the coefficients using that jawbone formula. We've got other formulas that we use after we get done with these formulas, and so I would really like to make sure that you see that stuff. Now before I begin, there's something here that isn't on what you've just downloaded. These little statements that I put on page 1, 2, and 3. First of all, the number of levels that we're dealing with for this model of nitrogen P cubed configuration can be easily calculated using the hook length formula. And I'm talking about how many levels are there counting the spin and the orbit. That means counting the 6 dimensions associated with a spin a half on each one of the 3 levels of P. So that's a unitary 6 that we talked briefly about last time. We're going to talk a lot more about its way of doing things today. And of course that's a bigger group than U3 cross U2, which is kind of what we've been working with so far, and we'll continue to do that today. But just figuring out what's the dimension that's associated with an antisymmetric representation of the states that would come with P cubed. That is something that would involve a vertical column Young tableau for 3 particles, 3 fermions, 3 electrons. And you remember how you did that. You take the 6 from the unitary and put it on the various diagonals of the tableau, and there's just the 2 lines here, the increasing by 1 across this way and decreasing by 1 as you go down. So it's 6 times 5 times 4 divided by the product of the hook lengths for that tableau, which are 3, 2, and 1. So we're talking about 20 levels here. So whenever you come upon a problem that involves some unitary groups, and we have a lot of them to go yet, particularly with molecules, this is a good start. See what kind of forest are you get into, how many trees are in it. Now there are other ways to look at this, of course, and we've been looking at it just in terms of the quartet. That's 4 levels with no angular momentum, and we'll do that first today again. And then the doublet associated with the P level, that's 3 times 2, 6 levels, and then there are 10 levels associated with the doublets that have angular momentum 2, the D doublet. So that's a quick way to get it. Now, suppose we had a bosonic system, and now we will have these for molecules. They're kind of rare because it's hard to find nuclei that don't have any spin. Carbon-12 is one of them, so we're interested in that. But this is a little bit beyond that. This is something with spin 1, that would be a boson, and that's U9, and if we had angular momentum 1 3 times in that, you'd be talking about 165 levels. But now you see the tableaus are horizontal. Same formula, but now the tableaus are all horizontal. for boson. That's the opposite of the fermion, you see. Now the real world for the pieces of that, both of them, are what we have to deal with today. So let's just go over one more time here, and I want to do it just to make sure that you see how it is that we use the lowering operators. And we're talking about right now Tableau 2.1, but we'll mention the other ones as we come along here. The other one is very simple. It's just the quartet S. So we dismiss it fairly quickly. But this one that we worked out in the last couple of lectures, and I've got the links to the beginning and end of the discussions of that active for clicking right there. But let's just look at what we need to do here. We need to start with the top of the food chain, as it were. We need to start with the biggest angular momentum, that's D, and we look at the doublets because that's what this tableau is shaped to give. And we're looking at a tableau 1, 1, 2, the very first tableau at the very upper portion of this thing, which we know, since there nobody else has a z component of 2 on this table except for that one, that this is the doublet d m equal to z component equal to state. So it's just a matter then of applying a lowering operator from angular momentum, the lowering L minus that we've shown pictures of and used for a number of things yet, and we'll be using that again and again. That L minus on an angular momentum state of orbital L and z component m is going to give you an extra factor, assuming these things in Ket's are normalized vectors. It's going to give you a factor L plus m, L minus m plus 1, the thing we derived by harmonic oscillator theory quite a few lectures ago. So here we are talking about 2, 2 being lowered to 2, 1, and that's just going to give you an extra factor of 2. So when we apply the unitary lowering operators, we need to put an extra factor of 1/2 in front of that in order to get an orthonormal state that has, instead of 2, 2, I'm reducing now to 2, 1. So here is that lowering operator going to work, and now we already know the matrix elements for this thing. The green one here, 2, 1, is that guy there. It's just a 1. And then this one right here, same thing. And when we figure out what the coefficient is, that's 1/2 times the square root of 2 that sits in front of the lowering operator. We get here 1 and 1 all over square root of 2. That's an orthonormal state. If it doesn't come out orthonormal, you've done something wrong. And there's a lot of checks and balances in the stuff that we'll talk about today that I should point out. So that does it nicely. Now, the next thing is to find out who else is occupying the m equal 1 slot there. And there are 2 tableaus in there, 1, 2, 2, and 1, 1, 3. Together, they're going to make the doublet P state with m equal to 1. So there are going to be 2 states with m equal to 1, and this time when we just get off easy, we go ahead and find the orthonormal state to this one, and that gives us that one right there. And then, of course, we're going to be lowering that one as we go along here. So I'm going to take you through the mid-level states and just point out where all of this is going to work. So the next lowering that we have to do on 2, 1 involves getting a 2, 0, but in the process of doing that, we're going to pick up a square root of 6. So in order to get orthonormal states, we've got to divide by the square root of 6. So 1 over the square root of 6 comes through here, and the square roots of 2 cancel the 1 over square root of 2 of the tableaus that we just got for the D21. That's this guy right here. And so applying the elementary operators, well, now it's not just 1, it involves some square roots of things, which I'll point out here. So we're going to be applying the operator 2, 1 to this tableau. We're going to apply it also to this one right here. So these are the 2 victims, and there are 2 operators that are in the lowering, so I have to do each of those. So I end up there with 4 tableaus and their coefficients, which we just read off. This one right here, we read off a square root of 2. Then 3, 2 is done twice on this particular tableau 1, 1, 3. And that's the thing not to forget, is that you should have that there. So the result then is this collection, well, 2 of which are 0 and 3 of which are what we want. That's, now we have the center of the D quintuplet, orbital quintuplet. And then we do the same thing with the P state. This is just writing the thing out in all of its glory. Okay, so we have a square root of 6 here hitting that, and this gives us just a couple of states right here that are the center of the D. And then the orthogonal combination to that, instead of square root of 3 over 2 and 1/2, it's minus 1/2 and square root of 3 over 2. So that's the doublet P with 0 angular momentum, center of its triplet, orbital triplet. Okay. And let's see if we got anything else here. If I want to lower, then just to check things, I can go ahead and lower again. This time, once again, I get a square root of 6, and the lowering of that then yields, well, we can look down here in this place here for 4 different numbers for this state. But it collapses pretty much. One of them just does nothing at all, and then two others are the same, so we have to add them, and that gives us back what we would expect to get, which is sort of the conjugate of the plus 1 z component up above that we were looking at right in this thing here. So we're back to having square root of 2 in the denominator, 1 over the square root of 2 twice for that. And of course there's the P doublet with minus 1 angular momentum. So we're going to stop there in this chain. We now have these, and we need to work with these. These are the things that we're going to do to build the spin orbit structure of the atom, and we're going to get pretty far into that today. But the main thing I want to do is show you the technology and make sure that you understand that. Now I'm also including here the quartet. That's for a trivial case, the 0-0 state, if you will, but it's got lots of spin. So we're going to be very interested in that first in the next parts of this discussion here. So remember what we're dealing with. If there's no splittings, no Zeeman effects, no spin orbit, we are stuck with those 20 levels that live in these 3 lines that we've already worked the Coulomb excitation or Coulomb energy for, and so eventually they're going to blossom. Now, one of the things I'm hoping to do, since I have so much work to do, maybe one of you, or certainly maybe TC, if you would like to try to actually do an eigenvalue plot for those 20 levels using what we've got, and in the process we'll be checking the arithmetic. Okay, so that's important. Okay, so as I said, the quartet S is this monster right here. There's nothing going on in the orbits. They're completely coupled up. And remember that the 1 is angular momentum, z component 1, but 2 is angular momentum component 0, and 3 is minus 1. So there's no angular momentum. That's what you use the letter S to designate in spectroscopy. And it stood for sharp, but that doesn't help you much when we're doing the arithmetic here to know that. In any case, basic idea is that this is a very interesting state beyond the quartet, and that is the highest D. But now we're talking about what kind of spin does that thing have. So here's where we get to use the gift from the Reviews of Modern Physics, which is on tops of desks and things here, which I have Xeroxed, and we're looking at pretty close to the top of that table for angular momentum 2, that's our D, cross the spin a half that goes with
the electrons that are going to be there. So we're going to be putting together a spin tableau as well, and the spin a half is what is allowed by the Pauli principle here. So this is a doublet, and here is the thing that's got a plus a half spin up, going with the highest angular momentum z component that you could have here. But in the process of doing that, there's just one state with a total angular momentum of 5 halves, and it's got a z component that's the sum of 2 1/2. That's 5 halves. So there's just one Clebsch-Gordon coefficient there, which we don't have to worry about. We just write the sucker down here, and we're in business as far as that very top state goes. But I would like to know something about its tableau structure, because that's what we're going to be using to get the U6 Slater determinants. This is going to come apart for us, or most of them that we're doing today will be coming apart. So the next stop on this train is one that has one step down in the coupling here. And this time I have 2 states that have coefficients that are given by the Clebsch-Gordon table here. We've got a 5 halves, 3 halves, so we're going to continue the 5 halves total angular momentum chain all the way through. We would go, if we went all the way to the bottom of the table, we're going to stop in the middle with this. By then you may be asleep, but we'll wake you up for that. So the basic idea is 1/5 and 4/5. It's kind of interesting is that the big I gets to have a small number, and the little spin's got the big part of it, 4/5. And remember, all of these numbers in these boxes that are actual Clebsch-Gordon coefficients have a radical over them that does not include the sign. There are no imaginary numbers here. So they just didn't want to write little radicals everywhere on the table. So that's understood with many of the more streamlined Clebsch-Gordon tables that you can find. But this one from Reviews of Modern Physics is better than any that I have seen for practicality. That is, you get a whole bunch of tables that are just on one piece of paper. So here we are using them, producing this state that has 3 halves for its z component, right? And there's another way to make 3 halves, which we have to look at, that goes with this one, okay? But before we do that, we've got a lot of tableaus to worry about here. We've got to take the square root of 1/5 and multiply it by this particular tableau, 112. We've already seen it, but now we got a 122 that's going to be coming in with 2 spin tableaus where I have the spin up instead of down. So this is the one with -1/2, and you can see the -1/2 right there, and then +1/2, the spin up that's associated with these guys, arrow up. And remember that arrow up, arrow down cancel each other, so they're paired, and you can forget about them. All the angular momentum is coming from whatever's hanging over the tableau there. So you have to multiply this 4/5 times the 1 over square root of 2 that's in there, and be careful about that. This one has just got the 1/5 sticking out in the open, so it stays, but then these guys turn into 2/5, and that should be an orthonormal combination there. 1/5 plus 2/5 plus 2/5, 4/5, 0.8 plus 0.2, that's 100%. So you got to check. This is, every time you do something like this, you got to check to see that it is actually giving you an orthonormal state. So it keeps you out of trouble if you do that. Okay, so the next stop, of course, is the orthogonal complement to this. That's the state of total angular momentum, 3 halves, with 4/5 and -1/5 sitting in it. So here we have both of these with angular momentum z component 3 halves. Okay. Both of them have 3 halves, and then the next one's going to have both a half, and so on all the way to the bottom of the table if you were to continue this for a while. But we needed tableaus for that too, so that's the other part of this, and now we're looking at the tableau here associated with the orbital part, and then the spin parts are attached to each of those tableaus. So the final result is this guy right here. So what I'm doing is I'm going to be collecting these guys, because these are the guys that we need to apply the, well, I call it the assembly formula. It's actually a disassembly formula, the way we're going to use it, but that's a very powerful way to look at all of the symmetry and anti-symmetry that plagues us for problems like this. Okay, then the thing that we haven't been doing here is 1 cross a half, the easier, smaller Klipsch-Gordon coefficient. The thing that have to do with the doublet P. Starting with 3 halves, that's the best it can do. 1 plus a half is 3 halves Z component. So the J, total J, is 3 halves now, and the Z component is also 3 halves. Now, it's probably a good idea to keep up on both these screens so we can make some comparisons, particularly when we're using formulas that show things on the other screen. So here's our starting point, and there's the first of the tableaus that go with the P. Remember, it has a minus sign, but square roots, 1 over square root of 2 in both slots there. The 1, 2, 2 and the 1, 1, 3 tableaus that were the number 2 and number 3 in that big matrix. Okay, so we have to make the total angular momentum 3 half states, and that means a combination of these two guys here, m equal 1, that's this, and spin component minus a half, that's this number right here. So that gets us 1 over the square root of 3 from there, and then this gets you a square root of 2/3, and that's got to be orthonormal. As these things swell up, they're going to multiply that to make more states, just like that. So that's the tableau picture, but it isn't finished yet because I've got to take the square roots that are associated with. And now we're dealing with those guys further down in the matrix, 1, 2, 3, the tableaus that have 0 Z component in the orbit. And these guys each have a 1 component. That is, remember, it's 1, 0, 0. So that's just 1 Z component quanta. And then this is 1, 1, that's 2, minus 1, that's 1 again. So that's why both of these things involve that number 1. And then over here, we're dealing with a 0 for the orbit, but we've got spin up. So we end up with the same Z component associated with the 3 halves. Okay. All right, so far so good? So making sense? Okay. Well, there they are with the numbers that go with them. Okay, so that's a pretty big, it takes a bit of work to get that guy. And then the next stop here is to look at, instead of J equal 3 halves, and I'm actually recording this up in the corners of these things, and I can see that this particular screen, for me, it makes me hard to see that. But this J equal a half is the rest of the doublet system for the orbital angular momentum of 1, L equal 1 now. So we're taking the Russell-Sanders LS guys and making LSJ states out of them. Okay, let's see if there's anything that's going on here that's anything different than what we've already done. It's pretty much the same. We're just pulling the lower row here and the extreme column here. That gives me 1/2 total angular momentum. All this stuff giving me just a half total angular momentum. Okay, and there is the result of using the tableaus to describe the state that is contained there, and then doing it again for that one right there. So we end up with pretty much something that looks very similar to that. Should be orthogonal to it, should be orthonormal, everything should check. And of course, when I was doing this at home, I very often come and it doesn't check, so we'll rip everything up and go back and get it going again. Okay, now, what are we going to do with this? What are we going to do with all these tableaus? We're going to process them using what I call the assembly formula. Now, this is really just a fancy way to take care of a whole bunch, and I mean, could be a very large number of Clebsch-Gordan coefficients involving spin 1/2. Here we're attaching or detaching spins, each of these arrows indicating a 1/2 quanta, and the tableaus indicating their symmetry. And we have written these states out in detail in the last lecture. And the question is, how do you convert those to Slater determinants? Because that's a really powerful way to handle this thing while taking care of both the spin and the orbit. And these are things that are really neat for doing entanglement thought experiments. Because when I have a Slater determinant, it's really easy for me to rip a part of it out. Imagine that something has happened to take two particles and just fling them away from the atom. Okay? And maybe one part has 4 particles, another one has 3 or something like that, if you're talking about a bigger shell than this thing. Off they go, maintaining some sort of coherence, some sort of sub-entanglement. So this, if you want to play with entanglement, boy, there's no limit to what you can do with this sort of disassembly. And then when they come back together again, the question is, what's it take to make them? So this is an orthonormal matrix right here between Slater's and a particular subset of all the tableaus that we would have in this P shell. Okay? And how do you get it? What does it do? Well, perhaps it would help if I detail the simplest example of this. That is, how do you get these two Slater states out of what we're used to, the para symmetry, and I don't care whether it's a diatomic molecule or what we've been talking about, the two components of a p squared shell. Okay, here we're talking about carbon's p squared wave functions. And here, of course, it's fermions, so I've got to put a symmetric with an antisymmetric, or I can put an antisymmetric orbital with a symmetric spin. Okay? And in particular, right now, we're talking about those that have spin 0, where there's a bunch of entanglement going on here. Okay? How do you get those numbers? All right? It's not as easy as it sounds. I think I soft-pedaled this in the last lecture. I shouldn't have. This is going to take a number of slides to show what is there. But when you're done, you'll see what it is you have to think about, or what you have to do with this incredible entanglement exercise. So now I have a really detailed discussion of the simplest assembly. Okay? And this is how we're going to do it, because we might as well use the symbolism that we're going to use for the Slater determinant states. That is, the U6 states are characterized by, it's almost like the ladder 6 of the hexadecimal system that you use in computing, right? After you've got done with 10, you go A, B, C, D, E, and F, right? Okay? We only have to go 4 here with this thing, but we're going to have to go all the way up to F as we do our U6 stuff, okay? But it's you know, we stopped using arrows at that point. We used to have A, B, C, D, and Fs in columns, right? And that's what you rip apart, you see, to study chemistry even. I mean, chemical reactions are going to experience coherence as well. So it's worth thinking about. So let's just make sure we understand what the tableaus are telling us, okay? This one, symmetric combination and orthonormal. Okay, well, whatever 1 and 2 mean, it's 1, 2 plus 2, 1, and then normalized. And this thing right here, well, we know what spin up and spin down are, so this is up, down, and down, up, but with a minus sign because it's a horizontal box, right? And then this one has a minus sign for that horizontal box. That's the orbital antisymmetry. And then there's the symmetry that has to go with this up, down, plus down, up. Okay? So I want to reconstruct what's behind this table down here. Okay? Well, the Slaters are not very difficult to write out. Okay? 1 up is A. 2 down is D. A and D. Okay? Sort of opposite ends of our state key here. All right? And then that's what we have here, A and D. But here I've got B, that's this guy right here, and right next door is C, that's this guy right here. So I've got A over D, and then this is B over C. They're both antisymmetric, so this one is AD minus DA, this one is BC minus CB. Now I'm actually thinking about the states that are represented by those, aren't just numbers. Okay. All right, so what happens in here? Okay. Well, first, what happens under here? That is not so easy to write out. So let's go ahead and do it. Okay? I'm just going to put these guys together into A, B, C, and D's. All right? So this guy right here is going to marry that guy right there. That means I'm going to get an up followed by a down for a 1 following a 2. Okay? So the little lines show you who got together to make these 4 terms. 2 times 2 is 4 terms. Okay, does that make sense? All right? So there they are. Let's give them the names they deserve. This is AD, this is DA, this is CB, and this is BC. So that's what we're seeing right here. Okay, that's the result of doing this, which is this, right? That makes sense? Okay? Oh, we just have to do it again. This guy. Okay? When you put this one together, and now we're making this one symmetric, that one antisymmetric, we get signs in different places. Okay? Minus, plus, minus. Well, plus, minus, plus, minus. This one's plus, minus, minus, plus. Okay? And that's what goes here. Okay? So now what we have to do is we have to remember these are double Ket vectors, and they're going to be orthogonal to anything up there that doesn't look like them. Okay? So DA is orthogonal to AD. Okay? So when this thing goes and multiplies this thing, only thing that it can do is get a number from the AD going to the AD. AD is not going to pay any attention to the other guys. Okay? But DA is going to do the same thing. It's just going to look at that one. Okay, so that's what we will be doing here. And basically what we're doing is we get one number for this one and one number for this one. This is a minus times a minus, which is a plus, and the two numbers are just 1/2 of 1 over the square root of 2. Well, add that up and you get a whole square root of 2, so that's the first number in our assembly table. Okay? You see what I'm doing here? Okay, so that's important. This one, very similar. You would think, where don't I get a minus from doing something? Because you get, well, it turns out the 2 minuses are canceled. You don't get one until you do down here. Okay? And you can see here, the minus CB is coming up to a plus CB, and the BC is also coming up to an opposite sign. So the whole thing is a minus sign, but the same number. And then you're back to plus signs for the last one. Okay? That's a long story, but this is cool. I mean, this should be in every quantum textbook.
I see it as reminiscent.
They don't use tableaus, that's the problem.
You mentioned states.
Yes.
So now this is our preferred method for determining the states in this system.
Yeah.
And we're transforming to something else that might be a little better for doing operators. Like, kind of like we did before.
And we just started that 2 lectures ago, where I showed the operators that involve the VVs, right? Vector vectors, or you could go ahead and do tensor vector and tensor tensor, right? There were 36 of the suckers, right? Because it's U6 and 6 squared is 36. And we're just going to need 4 of those to do our spin orbit. We just work with the 2 vector combinations that are available, plus the middle one, so that makes 3. So we're going to be able to do that. That is not coming today.
We'll be able to get to it.
Yeah.
From what we
We'll be able to walk into that really quickly. So now you get some idea of what it is that this is giving. And then as we go to bigger and bigger things with more and more variations in tableaus up there, all kinds of assembly matrices rear their, depending on your point of view, ugly or beautiful heads. Okay, so that is what we're after here. Okay, let's go ahead and keep up with what we're doing right here. I think that's the end. And now I will need the 2 to compare things as we go through this. But what I want to look at is how do I disassemble this tableau? And that's what this table is all about. Okay, as it says, assembly formulas for combining orbitals, it's also for taking them apart. Each column state is a Slater Determinant, left-hand side. Okay, it has definite spin arrow on each orbital state number. So what you have to do is stick those spins on the numbers that have them for whichever of these numbers. I'm going to go for this one first. You have. So we're going to be looking at that first Slater thing there. Okay? I'm going to put a spin up on the 1. I'm going to put a spin 2 with a 1. Okay? That 2 needs to have that particular spin. And then 3 has got to have whatever is showing here. Okay? So that's the first step. That's what it means to first write spins within the thing exactly the same way. That's kind of vague. This, I think, makes that clear. Okay? Now, the next step is to rip off the biggest orbit. I should say the most advanced orbit. This is actually the least orbit. This is 3 is equal to -1. But whoever came last, last in, first out. Okay? So what I'm going to do here is I'm going to be ripping off a box that has a downspin in the second column. That's formula C. Okay? So formula C is going to give me a coefficient, a factor, just a factor. You still have one more step to go to get the other factor, but C is the deal. And C is weird because it can give you a plus and minus phase. If you rip stuff off of the second column, you almost always have a 50% probability of getting a minus sign. But you never get it if you rip it off the first one. There's no phase for that one. We'll see that in just a minute here. But so I'm going to be using this formula here to give me a factor. And the factor is the number of ups, the number of spin ups, there's 2 spin ups, minus, and here's the thing, if you're going to do this stuff, you almost have to write down what the mu1 and mu2 are. Just write them down so that you don't make a mistake. I tripped over that so many times. Finally, I just did it, and then everything went smoothly. So here we have a mu1 for this tableau of 2, and we have a mu2 of 1. Those are pretty standard notations for tableau column lengths. Okay, so 2 here minus mu2 minus 1. Mu2. Let's see if mu2 is 1. Nothing. Okay, and then down here, mu1 minus mu2, that's 1 plus 2. That gives me a 3. Okay, so that's first factor. Then this is gone, and we're just pretending all the tableau we have left is this U2 guy there. This is the next box to rip off. So we're ripping a spin up off of the first column. That's this. That's B. Okay? That's the B formula. All right? And the B formula has no phase, but we do have a mu1 here, which is 2 now, minus the number of downs. Okay? There aren't any downs. So that's pretty easy. 2 minus 0. And then the denominator is mu1 minus mu2. Well, that's 2 for this guy, okay? And then mu2 for this tableau, this guy is out of here. I should have had that grayed out or something. Is 0. So I get 2 minus 0 there. I get a 1 and a plus. So I could have just stopped with this. The answer is in this one. Okay? That's the minus 2/3. All right? So it's that kind of thing. Here, real quick, is the next one. Okay, this one uses the other formulas, D and A, instead of B and C. Okay? It comes up with a 1 over the square root of 6. This time, everything's positive. So, that's how this works. Okay? For what it's worth. Can we make something that's better than that? Yeah, I'm sure we could. And also we could make one that goes with a spin, not a half, but any spin. Okay? And it also works for bosons. I mean, this is where we really need some nice mathematics to come along and do that. Okay, so we're actually almost done here because mainly what I'm going to do here is just show a little bit of the Slater determinants. Just a little bit. This one is pretty easy. I don't need the assembly formula for this one. You could see what it was giving 1 over the square root of 3 for all three. But this guy here is really just A, C, E. Now, here's the state key, in case you forgot, for this one. Okay. So instead of putting all of this garbage in every ket, we just put that. Okay? But you have to be careful. You have to see that that really is A, that really is C, and that really is F. Okay? But once you've done that, then it's going to be easy. We can have great big long Slater determinants and rip pieces out of it, or rip the bottom off it, or rip the top off even, and it doesn't matter. You then just use the symmetry of whatever's left in your pieces. And it's maintained. I mean, that's the magic of this. That's the magic of the experiment. When you go and have something separate, a beam separate, right, in a beam splitter, right, it somehow manages to maintain something that's oscillating and beating in a certain way. It just can't stop. Okay, let's look a little bit at what's involved here. And this one is kind of weird, but nevertheless, this is what makes it a little tricky. And by the time we do this again, I'm going to try to work that trick out. But basically now, what you find is nobody's telling you which box to put the spins in. You're going to have to let the assembly formula tell you that. Okay, that's the fly in this ointment. The thing, it's a powerful formula, but it requires a little bit of thinking about what you're going to get. Now, at first you might say, oh, I know how to make the tableau with the spins in it. I just take this tableau and put it right on top of this one. No, you don't. Because when I take this one and use the assembly formula, which happens to be A, I get a big fat 0. So, you're not going to do that. Not going to work. Okay, well, what are the choices, all right? Well, the next choice I see here is let the 2 have a spin up and make this guy have it down. That works. Okay. Now, this is kind of weird because it's got a plus 1 over the square root of 2. That means somebody else somewhere wants to play with this state. But we're going to have to put that discussion off a little bit. Okay. So what we're actually looking at here, and I'm just writing this thing out real quickly here, as the Slater that goes with that, A, B, and C, and pretending that square root of 2 didn't come up. Well, anyway, from here on out, it's just a matter of using these things. They're not, most of them aren't as easy as this one, but all of these need to be taken apart carefully to give the Slaters to go with them. And when we have that, then we'll be in the business for taking care of spins in orbit. Any questions? We've got plenty of time. I made this short. I'm not going to go and discuss any of the weird stuff. We'll take care of that in the next lecture. Okay?
Can you go back one slide?
Pardon?
Can you go back one slide?
Sure. No problem.
There.
There we go. Yeah. Yeah, this one
Can
needs
you
to...
have-
The other possibility that I have to here that makes sense, I can't have a 1 up and a 1 up, so that's out.
Yeah, I was
But
gonna
there is
ask
one
that.
other that I can have, and
You can have one down and one down and one up?
Yeah.
Sorry.
you got to have these different somehow, either by being 1 and 2, then they can both share, or I can have them be 1 and 1, and then it has to be up and down.
Combination B is not possible, right?
Having them equal is not good.
How about, well, it violates the Pauli principle, right? Because they are in this, they are in the same.
Yeah, at this point we're
How
we're
about
using,
this though?
Yeah, when we get done, we got to have a straight box.
Okay,
That's
combination
the only
A,
thing that's allowed for these fermions, right?
combination A is not possible either. Sorry.
Looked good. Looked like it would,
How about the
would be,
horizontal though?
but the assembly form you gave me 0.
But how about this? Like when, how about if you have like up in the
Oh,
horizontal?
I mean, you look at it. And say, I know it can be equal in the rows, and it has to be different in the columns. I've got a tableau. It says So that one doesn't work. And that's what's cool about this assembly form. Sometimes it surprises you. So the simple rules is having it equal in the rows is okay. Yeah, if you don't mind getting 0. So that means it doesn't exist. So. Now we're going to be doing this with nuclei and molecules. This is how we get to be able to do what's called hyperfine structure for molecules. But this is just plain old spin orbit structure, which is also called atomic fine structure, but it's not so fine for the light atoms. And that's because the electron is a comparatively huge magnetic moment. Gyromagnetic ratio 2 point something, right? Okay? Now what's really amazing is nucleons, particularly the neutrons, most surprising, has a magnetic moment. It's neutral. How does it get a magnetic moment? Okay. Well, the same way a molecule gets it when it's neutral. As long as the charge distribution is not uniform in the radius.
It's a neutron, right?
See, suppose I have more negative charge in the nucleus out here on the peripheries, and the positive is for some reason staying close to the center. You spin that guy and you got a magnetic field, right? And that's what we're going to discover about all the molecules that we watch to spin and make hyperfine effects, is they're all neutral, but the charge distribution in there between the protons that are the nuclei and the electrons which are the bonding is nowhere near the same, right? Kind of on the average it's the same, but it ain't jellium, which is what they thought atoms were before Rutherford showed us that atoms have nuclei. It isn't jellium. Jellium, it would be all neutral, and it's neutral everywhere. And you can rotate it or translate it, it's not going to give you anything. Now that said, the neutron's magnetic moment not 0, but extremely small, and proton is very small. basically the magnetic moment, gyromagnetic ratio times moment and all that, basically that goes inversely with rest mass. So the electron's there with its 500,000 electron volt rest mass. It's the really light fellow. 1836. That's very close to 6 pi to the 5th, by the way. We've talked about this before. Weird numbers that come out, you know, to be good mnemonics but have no physics behind them. The 2000 basically is the ratio between the kind of moments that we get with SF6 or a CF4. Any fluorine thing that has a spin of half. It's got a pretty big moment for a nucleus, but it's nothing compared to an electron. And here's something else about the molecule. The electrons are going, typically in hydrogen, they're going at the fine structure constant, 1 over 137, times the speed of light. So they're zipping. Well, carbon and nitrogen, they're out a little further and there's not as much charge to drive them. So they're, you know, probably hundreds of that. But still, they're really zipping. This thing is just taking its good old time rotating microwave frequencies, right? Okay, so this ain't hardly moving, and it's got no moment. So that's why you're going to hear in the next few lectures why it was Hertzberg that said there was no such thing as a rovibronic species mixing. And we'll see that rovibronic species mixing means something's happening with those hyperfine creatures, the nuclear magnetic moments and the rotation of the molecule. But rotation and vibration, that's the way the thing can get a little speed, right? If the nucleus is doing some vibration, right? And it does. And the Coriolis effect makes it do that. So you're going to have a first order effect of that in these guys, which we have to talk about. But the whole idea that the individual symmetry species, the things that really measure the nuclear spin configuration, should be totally inviolate. That was Hertzberg's rule. All 4 of his books say that repeatedly because the moments are so exceedingly tiny. That was his verbose way of saying, forget it, fella, you're never going to see it. But our clustering, you see, has brought these levels together to within, well, you have no limit, it's exponentially, depending on how far they have to tunnel in the angular momentum in the RE surface. So that's what makes the hyperfine effects enormous for certain cluster states of these high symmetry molecules. So that's why we want to really understand the kind of stuff we're talking about here today and in the next lecture on Thursday.
Which you really want.
And
So next we meet on Wednesday, right?
right, there's no weird thing happening. Only thing I can think about Wednesday is thunderstorms. Right.
Boy, the river
And
is
while
up.
we were having that seminar Friday a week ago, did you notice that there was a strange sound outside?
This Friday?
No, not the one where we had the honors. The one that came before that.
Yeah.
Did you?
Yeah, I thought that was a thunderstorm.
It was a thunderstorm. It's also a high-level tornado went right over us.
Really? A tornado in sky?
Yep.
You had one skip down right there before the tower was there. At the street.
It really made a mess down in Mountainburg, which is only about 10 miles south. And I was just driving south yesterday, and you can see all along the freeway, trees just laid over.
But there's no touchdown, right?
Touchdown there.
Oh, it touched down there? Okay.
Yeah.
I
But
thought,
here it just was overhead. But you could hear it.
Yeah. Oh, I thought it was a thunderstorm. I didn't know it was a tornado.
Right, like, that
Yeah.
was like the
You could
weird
hear it.
sounds that-
Did you hear it?
Yeah.
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 They were like.
I thought it was a motorcycle.
No, I thought it was a
Starting up early.
thunderstorm.
But
Yeah,
it was too steady, you know. It sort of and had, lightning and thunder with it.
But we don't get as many as Oklahoma gets, right? Not as many.
There hasn't been a really devastating tornado in Fayetteville since Civil War.
No.
But on either side of us, huge.
Yeah, it's just.
We're on a
probability.
Symmetric, the so-called southern tornado alley, and the northern, we're right at the Symmetrics.
Ah,
It has nothing to do with our mountains. Our mountains are tiny
Oh yeah.
compared to what it takes to change big level weather systems.
so it's more just the interior
No, it's
Yes.
just
shape of the interior.
We're very much the
oh no, we
interior.
get winds
Yeah.
from both like. Well, this is a region where the hot and the cold air mix, and that's what causes.
Well, it's moisture coming from the
Sure.
Gulf
Sure, that's
and
really
hitting
dry.
really cold, dry air
On
coming
the
from
other
the
side.
north, and makes this
That was a terrible
country the most tornadoes by a factor of 10. I don't think even China has as many tornadoes as we have.
Oh,
No.
Yeah, you don't have a gulf of warm water, blub, 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 that's what it takes. You got the cold air from the Gobi Desert, but you don't have the
Oh.
moisture. Yeah, you get hurricanes, but
Oh.
you don't. Yeah, interesting. Okay.
oh yeah, there was a terrible